Okay, let me get the password, the URL for the live stream.
Hello.
Hi.
Hi, hi.
I guess we can start whenever. So,
Okay, let's wait maybe 5 more minutes and then we start.
yep, sounds good.
is on.
Let's just wait maybe 2-3 minutes more to see if anyone joins, else we'll just start in around 2-3 minutes.
Okay. Can we put up like a text editor that says starting in 2 minutes or something?
Okay.
Just so some people don't leave, in case they don't see anything happening.
Uh,
Yeah, that looks good. Okay.
I think we can start.
Okay.
So, hello everyone, welcome to today's meetup on free monads. I'm gonna be covering free monads from certain points. So, basically, why are we even considering free monads in the first place? Why are we talking about them? How exactly does the free monad construction come into place? And we will look at some examples, one or two examples of how that works, of how to define the domain-specific language using free monads. And in the end, we are going to be talking about the performance a bit. I would have liked to cover the comparison of free monads with FX systems as well, but that is something I have not explored, so that's a part that will not be covered in today's talk. But otherwise, I think we should be able to touch all the required basics of what free monads are and how to exactly use them. So, having said that, now let's get started. So, why are we even? Oh, yeah, before that, if you have any doubts in between, just feel free to just interrupt me and ask. However, in the meanwhile, please make sure that you are muted so that no disturbance comes for anyone else. So, now let's get started. So why are we even considering free monads? Why are we talking about free monads today? In Haskell, the most popular or the most well-known technique so far, or something which everyone learns when they are starting with Haskell, or eventually learns when they start with Haskell, is monad transformers, or basically the MTL library. However, and that is basically used for doing effects. When I say effects, I mean anything outside of a pure function. So it can be pointing to a console or talking to a database or serving a web request, anything. Now, that's the most, let's say, well-established approach or well-known technique that has been there. So till now, a lot of the libraries are still basically monad transformer based. But there are also other ways of doing it. So one is this free monad, and the other are basically FX systems. FX systems, there are various libraries which you at least might have come across. So there is FreeRFX, FuseFX, Polysemi, and such libraries which are used. So basically we have MTL, we have free monads, and we have FX systems when talking about how to do FX in Haskell. And today we are covering the free monad part. So the first thing that we are gonna do is we are not outright gonna start with what a free monad is. We are gonna see something which free monads get frequently basically used for, which is writing domain specific languages or DSLs. And we are gonna start with one such DSL. I'm primarily gonna cover material from the article written by Gabriel Gonzalez on his blog, which is this one, Why Free Monads Matter. But some sections I will be skipping, and we will take some digressions in between to understand things which are not covered here uh, as part of this article, so that we can understand better. And then after that, we will see some example, a sample project, and we will end with a little bit talk on performance. So let's start with the DSL. So this is the same DSL which is also covered in this article. I'm gonna use the same DSL approach, and we will see other in the examples that we see, but we will be taking the same DSL here. So we have a abstract syntax tree or a DSL like this. This is basically, and it has basically got, let's say, 3 commands. So you can output something, you can ring a bell, or you can say a done. So that's all basically this toy language does for us. It doesn't do anything else. This particular next thing, this will become more clear in a little while of why it is there. But you can also see this data type as being defined like this. So we have a data toy B, and you have output bell and done. But you can see the explicit recursion that is here. So we are referencing toy again. So instead of this toy B, what we have done is we have taken a next here. This part becomes clear in a little while, so don't put so much focus on this now. But this what is basically our DSL is. And you could so it only does those 2 things, and you have basically the stop or the end instruction which is done. So a simple example for this particular DSL could be just this: output A, which is A becomes basically this B, and you're done. Or you have bell, then you have an output, and then you say done. Now, if you look at the types of this, you can see I'm checking what is the type of this here, and you can see the types are specified here. So you can ignore this part for now. This is not so important here. But for each of this program, so we have this program, and then we have this another program. Here we only do output, and here we say we are also ringing a bell, and then we are also outputting something. The type of each of this is different. So this is a toy car, toy B next. And this is some toy B1, toy car, toy B2 next. And this creates a bit of a problem in specifying or working with this DSL, since each basically sequence of commands that you specify, so you can have any n number of sequence of these three, the type of this will be different. Now, this makes it be problematic to work with. So one of the things we will start looking at is how should we go about fixing this. And how we go about fixing this will eventually result in how the free monad is actually defined. And one of the things to be more explicit here is note that in this particular DSL of ours, the end instruction or command has always got to be done. So if you want, you can have any number of output bells nested, but the end has always, if you want to end it, you always need a done command. So that is something to keep in mind, because that is also one of the things that we will have to, let's say, solve a little bit in a little while. So that's to start with. Now, how do we go about solving this? Before we jump to that, any questions so far on the DSL itself? Okay, so let's go and look at something what is called as a fix. So there is a data type defined here called fix, and we'll see how this works. But if you now use this fix on the programs we defined earlier, so you see this one has now been modified to use fix like this here, and this one has been modified to use fix like this here. Now, if you see the type of this, you will see they have the same types. Fixed stoica. We don't have this anymore where if you changed your command sequence, the end type turned out to be different. We don't have that anymore. So that is fixed by the fix. But how does this work, or what really is this fix? So to understand this, we will take a little bit digression into maths. So we will cover the concept of what is known as a fixed point. The earliest, I'm pretty sure all of us would have studied fixed point at some, we have encountered fixed point before while studying trigonometry in school. The simplest example of a fixed point is the cosine function. So if you remember for the cosine function, we have something like this. So you can say cosine x is equal to x, and the point or the x at which it happens is comes out to something like 7, I don't know, yada yada, something. So this is basically the concept of fixed point, where you take some function f, it can be any function, and fx, when fx is equal to x, we say basically x is the fixed point of that function. So for the case of the cosine function, this is 0.7 something. But in its simplest form, this is basically what a fixed point is. Now, how does this concept, this fixed point, exactly helps us in this, or why we are talking about this? So let's look into that in a bit more detail. What I'm doing here is I'm importing a library. There is something called as a control monad fix. This is the URL for that, and you can see fix is defined something like this, or you can, if you want to write it out like that, like fx is equal to fx form, we can say like this: fix f is equal to let x is equal to fx in x. Now, how does this construction exactly help us? So let's see the simplest recursive function here. So we are all aware of the factorial function. So I have defined, what I've done here is the factorial function is defined using a let. I'm saying this is the factorial function in factfy. So I think this should be straightforward. So we have the base condition, the terminating condition of a recursion, and then we have the non-terminating condition where basically this is called recursively. Now using fix, you can define it like this. So what this has been done is we are using fix. You can see it, the first thing is a function. So what we do is we take this and convert into an anonymous lambda function here. It's the same construction, and we have a phi as a parameter. If basically I run this, so I can run this here, and you can see I get 120. So I get the same result for this and this. So they are basically equivalent. Now how is this exactly working? So what we will do is we will unpack this. We will unpack this anonymous lambda into this function. We say this is factic. Note that for this lambda function, we had these two as the parameters. So for here now, rec and n are the parameters, and the rest is the same. And this might be a bit difficult to read. So a good thing to do is check what its type is. So you can see this is the type. You can ignore the for all here for now again. We have two constraints on this. They obviously have to be numbers and have equality on them. So the first thing is a function p to p. Again, we take p. All these p are basically numbers, and then it gives the result p. So the first argument is basically a function from p to p. This is the number which you will want the factorial for. And then you have the rest of the definition. Now, if we go back to how we define the fixed point of the function, let's try to do the same for this one. So we will say f is equal to factic f. So in place of rec, I'm giving f, and then you had your n, so that now comes as a lambda argument, and then you have this rest. So these are, what this is doing is, in place of rec, I am substituting this f, and then the result is basically just, then the rest is your normal substitution. And this is basically equal to having the recursive function. So this is the same recursive definition which we had here. If you check this here, it's basically the same recursive definition which we defined before. But the difference here is we used a higher order function. So factic is a higher order function. Why is it a higher order function? Because if you check its type, it takes a function as one of its argument, and that's one of the requirements for being a higher order function. So this is a higher order function, and while trying to do the fixed point, we took this higher order function and made a recursive function out of it. Now, how is it exactly working? So to do that, what we can do is we can expand what fixed factic actually does. So what does fixed factic do? So we can just expand one by one. So fixed factic gets expanded as fixed factic, then fixed factic, and then you expand one layer. And then if you see at each level of expansion, what is happening is we had this lambda function, and this is the parameter now. So rec will basically take fixed factic, and you can see that happening here. And then at each level, so now this is our first level of the recursion. If you go down again one level of the recursion and hence on and so forth, basically this thing keeps on expanding. So what fix does is it takes a higher order function and gives you a recursion out of it. And because of this, so imagine if you have a language which doesn't have recursion, but you have this fix defined as part of the language, then all you could if you needed recursion, all you needed to do was use this fix and you could make recursion out of it. And the fact that this also actually holds, you can see, is if we explicitly do fix factic phi, we get 120 again. So this particular construction, this fixed point construction, so here we are writing it as a data type, here we have defined it as a function. But basically what this construction is doing is it can take a higher order function and it's basically feeding it to itself as the first parameter. So which is this rec. This is, remember, this rec is basically this P2P. So it's taking a function, it's feeding it to itself to generate the full recursion. And so ultimately we have this, and note that this is not a recursive function. This rec here, we don't know what rec is here yet. If you just take this as is, this is not a recursive function. But if you use it with fix and you give it a higher order function, so which is in this case factic, you can generate a recursion out of it. So the fixed point concept basically comes up in a lot of places where there is recursion. So for example, if you study recursion schemes, fixed point will come into picture. If you're studying the concept of what is known as algebras, if you go a little bit further, fixed point comes there. Then if you study a concept called the Y combinator. So all of us have probably heard of the Y combinator, right? The thing by Paul Graham and all. So that particular concept comes from the same thing, the fixed point of the functor. So the fixed point basically helps us take care of a recursion, and you could basically have a function which is not recursive in itself, but you can take that, use it at fix, and you can have a recursion using fix, which is what is done here. Now, why does this come in picture? So this particular let's say property of the fixed point function helps us with this. So we are only saying fix toy car, but this fixed toy car takes care of making this data type actually a recursive type. So if we think about this is basically a recursive type, and the toy B is being, you can see that it explicitly points to here. But in this case, we are just saying next. There isn't explicit recursion that you can see here. In any of the branches, in any of the commands, we are not referring to toy. But this next thing, when it gets feeded to the fix, so basically like this, you get a recursive data type. And the type of that always, because of how the fix thing works, it always stays to this fixed toy car. Though because of the construction, underlying construction, this is actually a recursive type, which of course also we can see here. So that's how basically the fixed point comes into picture. Though this particular thing isn't covered here, so that's why I wanted to digress and cover fixed point. So far, let's see. Does anybody have any questions on what we have discussed so far?
Yeah, I got one question.
Yeah.
In order to make use of the fix here, do we need to modify the data type, or how do we get that result?
Do you mean to say do we need to modify this toy type?
Yeah, in order to get the type we want. Yeah.
So as of this point, we actually have already modified it. So you can start with this, and to be able to use the instruction, the next will act itself to have the recursion like this.
Cool. Yeah.
So the data type, we are actually already starting with a modified data type. But if you imagine that we started with this and then we talked about fix, so basically to be able to use fix, we will do this modification. So from this definition, you jumped to here. Does that answer your question?
Yeah. Thank you.
Okay. Any other questions? By the way, I will basically be sharing the sample project that I will show you. It has all the links. It will also have the links to this Jupyter notebook if you want to play with it. Though mostly all the code is coming from here, but just to be able to play with it at runtime, I've put this in a notebook. So if you want, you will also be able to access that later.
Also, it would be it would be nice if we can get a description of how you set up the iHaskell environment. So
Okay,
send
yeah.
us instructions after this. Yeah.
Okay, sure. I will do that as well.
Okay, thanks.
I will cover that a bit basically at the end. So if anyone is interested, they can also set it up.
Right. Okay, thanks.
Okay. So if we do not have further questions on this, then let's move on. So till now we have got our data type. We saw how to kind of, let's say, fix it so that we can, without having explicit recursion specification, we have actually got a recursive data type, and we also are able to specify any chain of sequence of commands that we want, but without having basically a different type for each sequence. Because if every different sequence of commands has a different type, then I cannot work with it basically with, let's say, one single function which can handle this, since one program or one sequence of instructions is different from the other. So fixes that up, which can be seen here, and it takes care of the recursion, which is what comes with this next part and the fixed thing. So now we still have one problem. In this DSL, like I mentioned earlier, if you want to end any sequence of commands, no matter how many nested sequence of output and value you have, you always need to use a done command. So at the end, there should be a done command, else it's not going to work. But when we write DSLs in the real world, this might not always be the case. So maybe if your DSL is for some kind of a language specification, I mean an actual programming language having an AST tokens and all that, that maybe makes sense. But let's say if you're doing web development, we don't know what exact sequence of instructions what exact sequence of commands or instructions which we will have in our DSL, so we can't really have done all the time. So we need to do something to take care of that so that we do not necessarily need to specify this. So I can also just say bell and output A without specifying it done. So how do we do that? To do that, what we do is our fix was defined like this. That was the definition which we saw here. We augment it or we enhance it with something like this. So now it becomes a sum type. And we have another construction here which just says throw E. And we can define a catch function, something like a catch function, which has a type like this. If you look at this type closely enough, maybe you can see something particular, but we will cover that in a bit. But this is its type, and this is how it's defined. So the reason we are defining it like this is basically we want to say, let's say we have any sequence of outputs and bells, but even without specifying a done, I can just say throw something and break out of that loop. Or sorry, loop is the wrong word. I can break out of that particular sequence of commands. So there's an example here where it says output A and we throw an exception. You can see the type here. It's basically fix E toy car, and the E part is we just have defined some new type here, incomplete exception. And this can work with catch to basically just like break out if you want. So try catch incomplete exception done. And at any point, if you just say throw, basically, so I can also have, let's say, output B, but since I have a throw in between, this output B will never be reached. So we have defined that particular part explicitly here so that now you can ask like why do throw here? I mean, you could also do done here, but like we discussed, we need, depending on the DSL that we are working with, we might not be able to define crisp, clear-cut definition of what done actually is for that particular DSL. So that's why we have this throw concept now. So basically, if you say output A, throw exception, output B, you are basically out. You will be out of here. The output B will never be a part of your actual program. So that's how you fix the part where you need not specify a terminating condition for your DSL. And if you see here, we have also defined the functor definition. This will come in a bit of why we are doing here, but you can see how the functor definition is defined. So that's what we have done so far. So having taken care of that part, and if we look at this thing, this fix which we came up with, so the fixed point concept is, let's say, universal. We made an addition to it to have this particular thing throw. But this actually is already defined in Haskell and is what is known as the free monad. So if you look at the free monads definition, so I'll just copy it here. So we compare. It's basically the same thing. So your throw has now been replaced by pure, and your fix is free, but otherwise it's the same definition. So we came all this way and it's already defined for us. So now let's see what this free monad is. So at least till now we know how this definition comes into picture. What is the reason we have this pure in this particular definition, and why do we have this free? So this is the part which corresponds to the fixed point construction. So we understand the two bits or the two constructors which arise with this particular definition of a free monad. Now, what exactly is a free monad? So I was mentioning that if you look at the definition of catch closely enough, you might notice something. So let's see what is that. If you notice the definition of catch, it's exactly similar to what a monadic bind is. So the monadic bind is defined as basically this. You have MA to A to MB, and then you have MB. This is what your monadic bind is. And the catch just represents exactly that. If you see the correspondence, so fix EF is basically your M, E1 is A, and E2 is B. So this definition has an exact match on this. And if you look at the operations, if you compare it to the monad, so this is the how would you define the monad instance for this data type. If you see return is basically nothing but pure, or what, if you look at our construction, this is throw. So return is nothing but throw. And the bind operation is nothing but a catch. So this construction corresponds to the free monad, and whatever we came up with, we can see that it corresponds to the exact monadic operations as well, basically return and the bind. So why we are talking about free monads now? So what exactly this free monad is? So let's take a little bit of detour. So what a free monad basically does is, imagine you have a functor. You have some functor f. So what free monad basically gives you is, we will not go into a lot of theory, we will just look at the basic simplistic notion. So if you have a functor, any functor f, a free monad can basically take that functor and give you a monad. So to actually type it out, so there is some functor f. We don't know, that functor can be, that f can be anything. It has to be a functor, that's all that matters. If there is some functor f, then free f is a monad. And you can see that basically from this particular instance for this data type. Now, what does this, again, what does this give us? Like, what is the benefit? So now, if we have a functor, so for example, if we are talking about our toy language, we wrote a functor instance here. This is the functor instance here. So I can take toy B and make it a monad. So this is written explicitly here. So to type it out, toy B is a functor, since you can see the functor definition here. So toy B is a functor which we have. So if toy B is a functor, now free toy B is the monad. So now we have a DSL toy B. We had a functor instance here, and now with just these two, we also have a monad now. So now, what does this monad really give us? So before just talking about that in a bit, you can see some of the helper functions here, or basically how you would actually write it. So output basically takes some x, and you can lit it in the free monad using like this. So basically free output x and then pure. Same way for bell and band. But you need not write this yourself at all, because there is a lift f which is already available. If you have used monad transformers before, which I am assuming most of you have, so this is basically the corresponding lift f in the free monad thing, where you can take your DSL, which is toy B in our case, and lift it in the monad. So basically what lift does is it gives you a way to go from your own functor, your own DSL into the monad. And this is the more explicit version, but if you just use liftf, you could just write it like this. And if we check its type, you can see it here. So this is now basically monad free is your free monad thing. and you can see we have lifted all of these particular commands. So basically each single command in the free monad. Now what does this really give us? So if we have a monad, we can use the do notation, which is basically the syntactic sugar over the bind operation. So I can now say, since now I have a free monad, I am just saying free toicar r. This is basically your next. This is where the recursion thing comes in, but it is not explicit here. And I'm using the do construction, and I'm just saying bells subroutine bell done. So these are my operations in this DSL. I mean, you can have any number of them. This is just one sample. And now we have the do notation for free, because we had a DSL, we had a functor, and using the free construction, we lifted it into the monad, and now we have a do notation for free. And one of the things to note here, or one of the magic things to note here is, whenever we are talking about monads, we always think of effects. We think about effectful operations. Like IO is the most common thing, like IO monad, but you could also have maybe monad, or either monad, or a reader, or a state. But in this particular case, this particular free monadic thing, it's a pure value. There are no effects here. It's a pure data type. It's a pure construction of your AST. There is no effect here. This is just a data type. And this is one of the things which is before coming across free monads is something I had never thought about, that a monad can also be just a pure value. And that's what it is here. We have a pure value. There is no effect going on. There is no IO. There is nothing. And now that we have this particular program, because now this is like an AST, this is the AST or the DSL of your own language, you can make of it what you want, whatever you want to do with it. So one example just comes next is, basically you just want to print out the DSL. So that's what this show program does. You can see it, the show program is defined here. It takes, basically it's simple enough. We are doing some pattern matching, we are converting the strings, and we just print it. So you can see this program is exactly this one, and this gets printed. So, and this is just one interpretation of your AST. I can interpret it any way I want. I can say what bell does is actually ring a bell, or I can say output A actually writes to some database. There is no restriction of how you can work with this AST. You can write an interpreter which does two different things with exactly the same AST or data type. And this is where the free monads really come in. You will see them generally being talked about in the context of some kind of a DSL, and basically writing your own interpreters for it to interpret it any way that you want. That's the primary power of the free monad construction, where you separate basically how you interpret your AST with how you define your data. So the data and the part of processing the data or interpreting the data is completely separate. And for this exact same reason, one of the advantages that you will often read about is basically this helps in mocking. Since I can have completely two different interpretations, actual production deployment interpreter will be different to your mock test interpreter. So this helps in testing as well. Any questions so far? Okay. I'm assuming no, so going ahead. And this is just a sample example where basically these examples show that your free monad adheres to the monad laws. So I'm not going to this a bit. Now coming to the next part. So this is our definition of the free monad. If we compare it to how list is defined, basically if you are thinking of list in terms of consing operation, so a list could be, a list's definition is basically like this. And you can see the very clear analog between the free and the list data types definition. And you could define an alternative definition of list in terms of free, which is basically this one. So if you just, even if you ignore just all this, if you just compare this, what this kinds of gives an intuition is this, or basically one way to think about free monads is, we can think of free monads basically as a list of pointers. So this free part basically corresponds to your cons. So the free constructor basically does the job of appending a functor to the list, and this pure thing basically does the job of nil, or representing an empty list. So there is a clear analogy between conceiving a free monad as basically a list of functors. Or you can also think of that way as basically we define the DSL. Our DSL is basically an abstract syntax tree, and a list is nothing but a degenerative case of a tree. So the concept of a list and the concept of a free monad has a lot of analogy that you can work with. And you can also go a lot deeper by thinking of it from the point of monads and list. And though I'm not going to go there, but we will come to that slightly when we talk about performance. So now, having come this far, let's go one step further. So let's consider a different DSL. So this example is also from the same article. So we can have a request and a response like this. So let's say this is what our DSL is. But the problem with defining it just like this is you do not have a clear interaction or a clear flow between what your request is and what your response is. So to fix that, generally how you define the DSL is something like this. So we still have the next thing like we defined for the toy interpreter, but now depending on the command sequence we have something like this. So what this means is, for this particular look command, you can specify a direction as an input. It will give an image, and this particular function which we are providing here, this is basically a contract between you as the programmer and between what you can pass to the interpreter. So this will become more clear when I cover the examples. So basically what this does is the programmer can specify the direction, but the next part of the sequence, so that you can change by providing something different in each interpreter. So for one interpreter, I might say that this is an actual effect which will take place, but in my test mock interpreter, that can be different. This will become clear when I show the small database and logging example that I have. But the primary way, the primary reason for writing the DSL like this is so that you can establish a clear link between what your request is and what your response and the next step is going to be. So this is how you will generally write the DSL. And then we have the functor instance here. And then you can see a sample interpreter which has been covered in that article. And you can see one of the key things to look at it is basically you can see that we are just doing pattern matching. And the next part of the interpretation, you can see, for example, this G is basically this image to next here, and you can see the next part of the program. So the interpreter is basically recursive. So it's calling itself, and for the next step, you can see you have your G, and that image, because basically this G is your image to next function, and that is being passed to that. And this will give you the basically recursive interpretation, the next step of your program. So this is only one single step, but the next step is performed by basically the interpreter calling itself recursively. And at some point, basically you will probably have pure to just return it. So any questions so far? Before we move on to looking at two of the sample codes that we have. Okay. So then let's move on to seeing something better than a toy example. So I have included one example here. I have found this from some random gist on the internet. I don't have that actual link anymore, but I've included it here. So in this case, we have a simple like something which you can, a sample DSL which can be used to operate or work with files. We have a write, delete, copy, read, and log commands, and then for this case you can see the functor part is actually not written explicitly. You can also derive it, but for that you need the language extension. So actually I have not written that here. I will fix that because otherwise this will not work, so I'll fix that. And then you can see what we do is we write some smart constructors to basically take a particular command of the DSL and lift it into Monad. So you can see if we am looking at write takes two strings as inputs, and this is the basically next step of your operation. For this case, that is just a unit. But to lift this part into the free monad, we are using lift f. So this is your one command or your one single constructor from the DSL, and you basically write helpers like this to lift it to the free monad. So we have written, so there is one for all of them. And then you have your interpreter. So since it's a pure data type, you can just do a pattern match, and you can see what happens is this signature is key here. So for example, this is where your actual interpretation happens. So you take the DSL and you actually move it to IO. So from your free monad, you can see the result type is IO. And in this particular case, so for example, since we are focusing on write, you can see we have a write file path text. This write file will be the actual write file. And then we have this monadic sequencing, and we call our interpreter recursively again. And it's the same thing for all of them. And one sample operation DSL is here. So you have your write, you have your log, read from the file, then depending on what you have entered, you can just log or you can also copy. So this is again, there is no interpretation here. So this is a pure DSL. You are in the free monad. And then here, what this particular gist does is, it uses the interpreter, but it gives a nice example where it shows that you can actually modify the DSL to have a optimize operation in between. So you can see the operations DSL is being used here, but there is an optimize move operation here. So if we look at the optimize move one, so for example, there is a slight optimization as to what happens if you have an operation where you want to copy and then you have a delete. So what this does is basically before you even interpret this DSL which is specified here, you can optimize it, change the DSL and then interpret it. So since it's a DSL and it's a pure data type, you can do that. And that's a nice thing here. And it has both examples where the optimize happen first and then you do the logging, or you do the logging first and then you optimize. So both are there. So this is one nice example. Now moving on to the example that actually I want to show you primarily. So is the screen visible for everyone before I start this part?
Yep, it's visible for me.
Okay. So in this small project, what I've done is there is a project from Alexander called Hydra. So it's like a framework which he has done, and it shows different approaches to define to basically how you can lay out your project. There is a title, something which is called as a titleless final interpretation, which is there. There is a free monad thing. So what I'm doing is I'm actually building a small example, which is most basically in all cases similar to that project, but it's completely trimmed down so that I only have just 2 commands in my DSL, nothing more, and it's also much smaller, so that basically I wanted to use it as a way of understanding this. So basically I'm gonna reference this example, but if you wanted to reference the complete framework of the project, that will be in the README in the project link that I will share, which you can see. So let's start with this. So I have defined a DSL here, DSL method, and it just has two commands. One is I want to log, and the other is running a query to the database. So this is my DSL. Now, before we look at the top level DSL, let's look at the individual ones. So this is the logger one. So when you look at the project, the separation is like this. We have an interpreter and we have the language. So the language is where basically your DSL is defined, and the interpreter is basically where you interpret the thing of how you are going to work with the DSL. So looking at the language, so this is for the logger DSL, and basically you can have each DSL be a separate component in itself, which is a part of the larger top level DSL. So in our case, the top level DSL has basically log and database query, and we are now looking at only the logger part. So this is my logger DSL. I have defined it. If we look at it here, this is basically defined as an abstract data type. Here I have used the GADT syntax. You can see the GADT syntax language extension enabled here, which is a generalized algebraic data type. So what this gives you basically is you can write your data type by specifying the types of the constructor. You can be explicit about it. So that's what the GADT gives you at its simplest definition. So my log DSL basically takes text, and if you think about, so this is the simplest way of logging. I'm not doing any kind of structured logging or anything. All I do in the interpreter is take this text and print it. That's all the interpreter does in this example. So if you think about that, basically your end result is basically going to be IO unit. So the way I have defined is this unit to next, which is what I was talking about basically here. Or going to this part, basically you link what is your request. So in the case of log, the request input is basically the string or the text or what I want to log or print. And the next sequence, we don't know. This is Basically, the next can be anything, but we have written it like this. So basically, IO unit, we don't specify the IO here, but the unit comes and then you say, this is unit to next. And then this is the recursive thing where it references itself. Logger method f next. And then we have a functor, which we have defined. And then this is the monad. Now, if you remember, I had said what you do with free is basically, if you have a functor, the functor here is logger method f, the free, that particular functor is a monad. Now, in this particular case, you can see I am using something which is just f here. We will come to this bit when we talk about performance. So there is a particular variant of the free monad that I'm using, but for right now, you can think of that f as basically being free. So what I've done is I have written free logger method f, which is my functor. So this gives me the logger monad. And I have written a helper function here, which basically takes the text and lifts it into that monad. So lift f and this log message f message, and for this we just write id here. Basically, this part I am saying while specifying this smart construction as just id. This will become clear a bit later when we go to the top level DSL. So I have written this particular smart hell constructor or whatever we want to call it, so that this particular command in our DSL, we can lift it into this monad. So we have a lift f here. So that's what the DSL is. Now if we go to the interpreter, so I am saying interpret logger method f. You can see it again. This is a pattern match. I only have one command in the DSL, so that's all there is. This message is basically my string which we want to print. And if you ignore the rest a bit just for a moment, you can see all I do it with is print the message, nothing else. So if this was some more complex thing, you would do more here, but for this simple example, all I'm doing is just printing the text. Now where the rest of the thing comes is, which I was talking about when we are talking this, remember that basically this next is your function. So unit to A, where A is basically the next sequence or the next command in your DSL. We don't know what that is going to be. So this is basically polymorphic at this stage. But what it does is this next, we will just map it over this print message. So print message is basically your IO unit, and we do an F map so that whatever your next part of the DSL or the next command in the DSL is, this next F map thing will take care of. Now let's have a look at the DB part. So this is the SQL DB DSL. You can ignore the exception part here. I just took it, but I haven't really used it here. It's also there in Hydra, but I did not implement it here. So you can ignore it for now. So you can see we have our SQL DB method DSL here. The Hydra project uses Beam library, but which is like an ORM, but I have used the simple Postgres simple here. So this is different compared to what Hydra is doing. Of course, the logger is also simplified. So this is Postgres simple, and I have used that. So for that to run a query, what I need is I need my Postgres connection. I need my query string. This is basically going to be a query string. If you look at the Postgres simple library, and what it's going to give me is basically a row of results. So this is what your R is, but it is constrained by from row, and you can see basically all these things is coming from the Postgres simple library. And in this part, since our result is basically a list of row of results, you can see this here is not unit now. We have defined this part to be basically this list of R to next, and then again we have this recursive part of the DSL. Then we define our functor, and we have our SQL monad, which is free. SQL DB method F is a functor, so SQL DB is a monad. And we now, for this also, we define some helpers so that we can lift basically individual, if you have more, but here we only have one, but still. So basically this lifts the SQL DB method in the SQL DB monad, which is defined here. So we have used liftf. This action is basically this function which we are going to pass. And for this particular part, we are just using ID, like before. Now, in the interpreter part, if we go, so if we look at what my, so if we look at the interpreter part, so let's say I'm seeing what my runner is. My runner's type is this. So this is the function. I have my next as before. So ignoring the next thing here, you can see basically that runner, which is this function, will take connection and query and then basically run your DB thing. Now, it will not be clear here, so let's go to the top level DSL, which is here. So now when we go here, and specifically the same way I have also defined the DSL components here, logger, run query, and then the DSL monad, which is free DSL method, and then you have your interpreter, and we have the helpers. The key part to note here is here. So if you look at the query underscore function, this basically comes from Postgres symbol, and you can see that whatever gets passed here basically will change how your DB operation gets run. And we have our connection and query string as inputs, and they have been basically the run query DSL has been lifted into the monad, and then the interpreter is here for them. This calls the run logger, which is defined here. Now note now coming to this part. So we have the interpret method. Now we need to write basically what is your DSL to IO. So whatever DSL you have, you will define something which will take your DSL to your actual effect part, which if we look at the previous examples, for example, if we look at this one, it was this interpreter to IO thing. So basically this is the interpreter to IO. And note the fold F here. So this fold F is basically the opposite analog of your lift F. What liftf gives you is you take your functor and you bring it to the monad, and when you want to actually collapse your monadic operation to, so to speak, so you use the foldf part. If we look at its signature, you can see it's FA to MA. You can ignore the rest of the bits, but the primary part, though they are actually important, but the primary part is basically this. So you go from a free monad to your actual operation. For this particular case, our M is IO, but if you were to write a different interpreter, M could be actually just a pure effect and not an IO. So to go into the monad, you use liftf. To come back out of that free monad, you have your foldf. And same way, basically, in the top level interpreter, you basically call your the interpreters. So here I'm using the smart constructors, though it's possible to directly use the other one. But you basically call your foldf indirectly here. And so that's the interpreter which is calling the fold L of the individual DSL, and the top one is basically here. So you can see I have done a DSL to IO, which is just full def to your interpreter, full def interpreter, and the interpreter is basically your FA to IOA. So going to the interpreter part, this is a functor to IO thing, and the actual running part, or the where you convert basically this, what this full def does is, we were talking about a free monad is basically a list or a abstract syntax tree. When you actually want to now walk the tree and basically interpret each leaf of the tree or work with each leaf of the tree, that's where basically the full def will come in. So full def takes the interpreter, and you can think of this primary line is basically where your collapsing of all the monadic sequence will happen. Now, what this particular thing I'm talking about is basically, if you look, there is a very good answer on Stack Overflow of how to understand a free monad. So if you just look at the answer is given by John Bingley. So if we look at the monad, a monad is basically something that computes when monadic context is collapsed by join. Recalling that the monadic point is basically defined as fmap and join, and this is how monads carry context through sequential change of computations, because at each point in the series the context from the previous call is collapsed with the next. In a free monad, basically it does not do any collapsing at the start. We talked about when we were looking at the simplest toy interpreter above. This is basically your pure data type. This is just a data type, nothing has happened here. So this is that line. Basically, a free monad satisfies all the monad laws, but it does not do any collapsing. It just builds a nested series of context. The user who creates the free monadic value is responsible for doing something with those nested context. And that's what happens at this line, fold F. You basically collapse your monadic context. So the user who creates a free monadic value is responsible for doing something with those nested contexts, so that the meaning of composition can be deferred until the monadic value has been created. So this is basically your interpreter part. That your collapsing operation which you define can be different for your testing and for your actual production run, since the actual DSL is just a pure data type, nothing more. The DSL monad is basically a pure data type. And if I go to main, so here you can see I have defined a simple operation. So I have a log message, I have a run query. So here I'm not actually using any tables or anything to just keep it simple, but it does require and use the connection to an actual running Postgres instance on my laptop. And this runs the query, and then I log that query result back. And if I run it, so I do a stack run, you can see from here logging from inside the DSL, and this is the result of that query. So the key part here is basically how you define your DSL, and then the functor, and then you have your type. One thing to note here is, which came up in some of the discussions earlier on, is this logger here is basically a monad. So one question you might have is, why are we not using this here, this logger method F? It is possible that you can, instead of referencing the logger monad here, since what in this particular case, we actually have a nested free monad. So we have a DSL method which gets to a monad here, and we are referencing a logger monad here. But you could also write a logger, you could use the logger method F, or basically the functors of the individual DSL at this point, rather than referencing them as monads. So there is a performance simplification here, but if you want to keep that performance thing aside for a bit, basically the reason it's done here like this is the individual languages or DSLs are kept separate compared to your top level one. So basically, I can completely change this logger monad, and the top level DSL need not know about it. So kind of a separation of concerns thing, but this point can come up, or it can come up to you when you go further down the road. So that's one point to clarify. Okay. Yeah. So any questions so far?
I just have a comment on this, the thing that you just mentioned, that we are not
Yeah.
using the the functor part of it. We are using the monad directly, right? So we're using the logger monad
Yes.
directly. So an advantage of using the functor part of it, apart from the performance, would also be that we already have these things. So we have a construct called co-product that's already provided to us, and I think it's a part of the base library, right?
Okay.
So you can, so using co-product, you can combine multiple uh, uh, algebras like this DSL method and the logger method, those things together, without having to define that product ourselves. So just so the
Okay.
tooling is already provided for that, so it makes it a little bit easier.
Okay. 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 Yeah. So I'm not checked co-product myself, but that I'm definitely gonna check out. That would be nice to look at. So this part basically mimics how it's defined in Hydra, but though, like I said, these are completely simplistic. So for example, the query DSL in Hydra is much more complex and uses the Beam library, Beam Haskell library, and the logger is slightly more involved, though structured logging is not used there still, but yeah. But otherwise, basically, the construction or how it's defined should be the same. So I can show you. So this is the Hydra project. So let's see. So we have the logger, and you can see how the logger is defined here. So it's also taking a message, but it also takes a log level. And you can see, otherwise you can see the same construction. So if we go to log level, okay, my HLS is not working here, but so log level is basically just like your log info warning and all. I'm not using that, and your message is a little bit more involved than text, but otherwise the construction is the same. Same way, if you go for SQL, so the SQL one also has a single command here, but this one is slightly more involved because it uses Beam. So you can see it has more helpers and things compared to what we just defined. In our case, all we needed was basically this simplistic function which comes from query, which just takes it's a string but with some type level safety, but it basically just works with that. No more things. But the Hydra one is more involved and uses Beam and such. But the basic concept and idea is basically a stripped down version of Hydra. So any questions so far before we take 1 or 2 minutes break and then we move on to discussing about performance? Okay, so let's move on to talk about performance then. So one of the things, DSL is one of the thing which free monads are always come up in the context of. But whenever you are discussing free monads, something else will also always come up is the performance part. Now we are going to take. So I'm not going to go very in depth in the performance part because, to be honest, there are some more high level concepts that I myself don't really understand. But I'm going to cover most of the fundamental idea behind it. So when I started, I mentioned basically this F thing. Why I mentioned that instead of free, I'm using F. If you note above, this is coming from Control Monad Free Church. Just one sec. This is coming from Control Monad Free Church. So there is something called as a church encoding on the free monad, which basically gives you better performance than uh, the free monad definition which we saw here. So compared to the free monad, which is basically what is defined here, this particular F version, which is defined differently, gives you a better performance characteristic. Not raw performance, but mostly basically asymptotic performance improvements. So let's see how does that come about. So coming to performance, there is a very good talk from someone known as Raichu. You can look it up on YouTube. It's called The Free and the Furious. I'm basically gonna use parts from my understanding of that talk, and there is a 3-series article done by Edward Comet, which is basically about the performance of free monads. So the free library has been written by Edward Comet, and he has written this three-part series articles on the performance improvement thing. But what mostly concerns us is this first part. You can refer the other two parts also, but as such, they are not necessarily required unless you want to understand the construction that he uses in his library. So there is a paper from Janis Voitlin called Asymptotic Performance Improvement of Free Monads. And in that paper, he uses something called as a co-density. So don't get so hung up on the name. We won't go into that. We'll see how co-density is defined, and we will see a running example that it actually does improve the performance. So how exactly is co-density defined? So I'm using this code from Raichu's talk, and you can see the co-density is basically defined like this. So we have co-density MA, and it says run co-density for all B A to MB to MB. Now, for those of you who have not seen the for all construction before, the way to interpret is basically this function, whatever run co-density it's gonna take, it should be so A to MB, and our result is an MB, but in no way can we depend on the B part. So whatever this function that will be passed to this run co-density thing, which will be A to MB, should in no way depend on the B. So, and if you look at the actual type, so there is an implicitly hidden first argument to run co-density, which is co-density MA itself. Then the second argument is basically this, for all B A to MB. So this for all B is basically all it says is exactly that this particular function should be valid or work for all B's. Or the other way to interpret or see this as the end result should in no way be dependent on what my B actually is. So I don't know, B can be anything, strings or whatever, mini complex type. It should in no way affect the final result that you get. And that's what this for all B implies. And you can also see that basically for the B part is not mentioned in any way to your left side. So that what this run code density function is defined. So this is a, if we just look at the type as such, it's basically it's a function. That's all there is to it. But how does it exactly help? So we will first look at the point where does it actually help us. So in right to stop the code, he has defined various things. So what we'll do is we'll run the code and we will see whether this application of this particular code density thing, does it actually help. So the first thing to look at is we have an input. So the input is defined like this. This is basically a long list of chars C, which is just repeating. That's the input. The DSL is a teletype. So it's this. You have a put car and you have a get car, and that's all there is to it. You can see the functor instance is not written manually. We are just deriving it. And the monad part is written in a different way, but this is the same. You can think of it as the same way as this one, but it's defined differently. So this is our DSL. All it does is put and get char. And then our program or our actual DSL operations is this one, rev-echo. And you can see the helpers. So lift f get char, put char. That's what we are calling in our this particular sample list of DSL operations here. We do a get char. We have a condition, we recursively call ourselves, and then we do put char. So that's all there is to it. And now what I'm gonna do is I'm gonna basically run it. So okay, before that also to show you what run pr is. So run pr is basically this. So we are gonna run this and see, well, let's see, just run it and see what happens. So just printing, and it's gonna take a long time. And I'm just gonna jump here and show you the running times from his talk. If you see this simple one, it seems to take 71 or 72 seconds, and it actually, I've waited till 1 minute, but it definitely doesn't finish under 1 minute. So that's and this is basically your free monad thing. And you can also check, I forgot to show that actual thing. Basically this is the log type, and this list thing is it has been defined as a free monad. But in this particular case, the definition here has been lifted with code density. So let's see what happens if we apply the code density transformation. So I'm going to do the same function, but I'm gonna add one thing here called improve. If you see improve, it's defined here. So it's calling lower code density, and lower code density, if we go to that, it's defined here. So basically we are using this particular transformation or whatever code density is, and let's see what happens now. So it ran much faster. I haven't timed it here, but if we looked at the time here, it's on his machine, it runs on 0.72 seconds. So let's say this definitely at least runs somewhere under 2 seconds or 3 seconds. So we came down from something like 72 seconds to down to a few seconds. And that's a lot of improvement. So now coming back to the question, why does if we just consider this free definition, why is it not performing? Why does it have this kind of a horrible performance? So if you remember, we talked about basically list, and the same thing comes here. So if you look at the bind implementation of the free monad, the underlying one, or let's just look at the bind implementation first. Basically, monadic binds are like this. They are left associated rather than having something like this, which is a right associative way to define it. Now, if you're talking about list, so basically we are saying if you're talking about list, then if you're saying it is left associated, then we have basically something like this, instead of having something like this. So now this particular thing is what kills the underlying operation. Now if you look at the join implementation of free monad, which is this, what it shows is basically at a bind is basically an fmap and join. So each bind operation basically does not reduce the structure of the free monad. You keep on building more and more. Since you have this free type on top, it does not reduce in any sense. Or if I'm talking about list, if we look at this particular operation, the left associativity means we have to traverse this structure again and again at each bind that we encounter. And this results in the horrible performance of the free monad. What the codensity transformation does is, even if we ignore how it's defined, we can go look at the monad, how the monad definition of codensity is defined. And if you look at the end here, you can see in this particular case, what is happening is, this is the bind operation. So let me just show you the type. You can see the specific type here. The bind operation here is basically codensity FA, A to codensity FB, and then to codensity FB. Where if you think in terms of the simpler one, this is nothing but M, where codensity F is your M. So MA to A to MB to MB. So this is how it is. And what it does is it transforms this particular bind operation to a function composition. Now, function composition, when we talk about functions, function composition is basically right associative. So what this codensity transformation effectively does is, it converts something like this, if you are only thinking about list, to something like this. And this is where basically your performance improves. So like we saw after running this, just applying this particular transformation, this lower codensity thing, forget what exactly the types involved are here, but looking at this particular thing, what it's effectively doing is, it's taking the bind, which we have on our left here, left hand side, and turning it into a function composition on this side. So it converts a left of associative operation, which has a horrible performance, to a right associative operation, which, as we just saw now, has a much better performance. And this is what basically the F is doing. So the F that I use here, the underlying definition in the library by Edward Kemet is slightly different, which is covered in the next two articles of this. But basically, you can think that this is applying that transformation if you use this F here. So I need not use improve myself or this lower codensity transformation myself. if I use this church encoded version of the free monad, you should have better asymptotic performance than instead of basically if you were to use free. So that's why I'm using F here. If you look at Hydra, Hydra has both variants. You can see the church encoded versions and the non-church encoded versions. Right, just makes it. So if you look at the framework, you can see there is a free version and there is a regular version as well. So the church encoded version is in this free version. Hydra church free, and the regular free one is in this Hydra free. So performance is one thing that comes up a lot when free monads come up. If you even go to Reddit, it's one of the primary points of contention. Everyone says the performance is bad. But maybe if you use I don't have an experience myself of being able to compare both MTL, fuse effects on free monad implementations, but maybe at least you have a better performance than just using free. So that's why we use the F here, and basically that's where the performance improve. The asymptotic performance is better compared to your just standard free which is defined. And so that's where we can see the performance improvement. And if we just for completion's sake, if I want to show the church definition in the free library as well. You can see the F is defined differently here. It does not look the same as the code density one, or at least it does not use that improve thing here directly. It's a different construction, but the underlying principle is the same. You can also see that the improve function here is slightly different. So that is covered in the next two parts if you're interested, but the primary fundamental concept is that you convert your left associated operation to a right associated one using this particular transformation, since it changes it to just pure function composition, and then you have that particular performance improvement. Yeah. I think that covers all that I wanted to talk about on free monads. So, any questions of what we have covered? Anything from start till now? Okay, so I'll move on to just covering the Haskell notebook and the materials a bit. But just to close it off, so when you look at this full thing, it might not be directly clear what is happening at what place. So the few things to remember is, one is this particular next part, which takes care of that recursion thing implicitly because of the fixed construction that we discussed at the very start. So this particular one, and then so that's the part which is not obvious at all, and was not obvious to me when reading this article as well. It took me multiple readings to come to that. So that's one part to remember, and the other part to remember is basically I have not covered the actual functor monad instance writing of the free monad, but that is necessary if you want to understand basically what this. So when I'm writing fmap next here, what exactly happens? So what happens when we call fmap on this particular DSL method? So DSL method is the functor, but what happens with the fmap? So you need to look at the individual definitions. So for example, if I think I have it open with this. So the individual functor, applicative, and monad instances, this part is where the part of the magic also happens, since we are not calling the bind operation explicitly here anywhere, but when you do the basically when this happens, you do, and when it does get interpreted, the underlying implementations is where the magic happens. So think of it something in a similar way as if you are looking at a state monad, the sequencing of the state monad is not immediately apparent unless you look at the underlying monadic definition, monadic bind definition for that state monad. So the same is also applicable to the free monad here. Okay. So yeah. So the Haskell notebook thing, I'll be sharing the link of the sample project, which is this. It has a README, It has a README which has basically all the links and resources. I will add one or two more so that it also references the notebooks. So the Jupyter notebooks you can use for Haskell by using this. This is the basically that iHaskell project, and there are multiple ways to install. So I'm not sure which one works for people. There is a Stack and Docker example. There is the next one. So probably the Docker example is what will suit most people, I think. At my end, I am basically using the Nix one because it's slightly just easier. I already use it for one or more packages, but on my previous laptop, I have tried the Docker one, and I think it's more straightforward. So probably that's what people want to use, and then you can basically have Jupyter style notebooks and play around with your Haskell stuff in the browser. So yeah, that's the iHaskell part. Unless anyone has more questions, I hand it over to Anupam if he wants to add some closing words.
Just a quick question, not much,
Yeah.
maybe to the talk. You mentioned Hydra, and what's that? I just
Okay, yeah. Yeah. So there is a project by Alexander called the Hydra framework. So it's kind of he has a book on software design and architecture in pure functional programming, and this Hydra framework or project basically serves as a showcase for that book. So it has quite a few things. So like I mentioned a bit earlier, so for the same example, it has 3 implementations so that you can compare. It has final tagless, which is basically like type classes of effects. It has the free monad, basically the non-optimized, the straightforward free thing, and it has a church encoded free monad as well. So you can kind of think of it as basically providing a framework so that imagine if you had this framework. So, like in this case, this one. If you are using this framework as a library, you can forget about like all of these details, and all you could do was basically just write your application as a free flowing kind of operation sequence. So, for example, if I'm using it as a library, I do not care about defining all this thing. I just just write these 3 lines and I'm done. I'm good to go. I don't need to worry about anything else. So it basically provides a sample framework which maybe you can work with or build on however you want to use. So we basically used a variation of this Hydra project or a framework at work. It's not open source, but it uses the same concepts and kind of has the same structure. So basically, you can use the Hydra as a library, and then all you would do is just write your app using these smart constructors without having to worry about transformer stacks, composing, or anything. So that's what the Hydra framework is basically.
Okay, yeah, thanks.
Okay, Anupam, then I guess over to you.
Okay, great. Yeah, if there are no more questions, I guess we can then close this. Thanks, Sanchayan. This was pretty good. Uh, very informative. Uh, so I just like to plug the various groups that we have for functional programming meetups in India. So Sanchayan runs the Bangalore Haskell meetup group, and I run the FP India meetup group. So please join those and ask questions if you have any follow-up questions. All right. Thanks everyone for joining.
Yeah. If anyone has any feedback or questions, or again, I'm also learning this, so if I have done something wrongly and you find a correction, please feel to get back to me and let me know so that maybe I can also communicate to others, or we can talk it about on Telegram channels or such. So yeah, thank you everyone for joining. Have a nice weekend.
Thanks.
Bye.